Welcome to the Observatory Night. I'm really excited tonight. Thank you. Save your claps for these folks. So I'm Jonathan McDowell, and I'm going to introduce the speakers tonight. I'm an astronomer here at the Center for Astrophysics. I work on black holes and quasars on the Chandra X-ray Observatory. But I also have a newsletter about space exploration, Jonathan's Space Report. And so I've been interested in this issue of space travel for a very long time. So our subject today is interstellar travel. And, you know, when I was young, it seemed so easy, right? You just go, warp factor 5, Mr. Sulu. Or, you know, twiddle a few knobs in the TARDIS. But I'm here to tell you it's actually really hard. And we've known this for a while. In 1694, Isaac Newton made one of the first serious calculations of how far away the stars were. He sort of go, well, let's suppose all the stars are the same brightness, and let's look at Sirius, and how far away must that be if it's really the sun? And so the stars are much, much further than the planets. And a lot of people, everyone here knows that, but you know, a lot of the lay public I talk to, they don't appreciate how much further it is. If you're traveling at the speed of light in a starship, you go 7 times around the Earth in a second, and you pass Mars in a few minutes, and the sun is 8 minutes away, and you're zooming out, and after a few hours you get to Neptune and Pluto. And then you get out the Monopoly set, because it's going to be 4 years till the next star, right? And so, so you know, Sirius is 50 trillion miles from Cambridge, and it's true that as early as 1972, the first interstellar spaceship was launched. Pioneer 10 was launched past Jupiter, and as it picked up speed from its flyby of Jupiter, it started to escape the solar system, and it's now 100 AU or so away from the sun, and it's heading out of the solar system, as are Pioneer 11, Voyager 1, Voyager 2, and the New Horizons probe to Pluto. We have 5 human artifacts, and actually a few more, because some of the rocket stages, the New Horizons rocket stage is also on its way out. But they're going to take tens of thousands of years to reach the stars. So they're not going to be working by then. And so the very fastest things we have are totally inadequate to reach the stars. So it seemed with the advent of the space age that the stars were just out of reach. You needed some science fiction magic like warp drive or something like that. And the first serious technical discussion of actually how to really get to the stars that I know of was in 1978, when a group of engineers in the enthusiasts in the British Interplanetary Society published a report called Project Daedalus, in which they did a detailed engineering study of a robot probe to Barnard's star that would go by, you would throw pellets of helium-3 out the back end of your spacecraft and ignite them with lasers in H-bombs. And it would putt along with H-bombs with a big, like, concrete shield behind it. and that could get to Barnard's star in a reasonable time if you believe that it was possible. But really there hasn't been a lot of serious look until recently at actually going. But then, you know, we discovered extrasolar planets. And suddenly there's somewhere interesting to go. And that's given a whole new impetus to the idea of crossing interstellar distances. And so astronomers at the CFA are now involved in this radical new effort to develop starflight technology called Breakthrough Starshot. And this is an ambitious project, and it drew headlines because Yuri Milner, the billionaire who's funding this, got together with Stephen Hawking, and anytime Stephen gets up, you know, the media like crowds. Okay, Stephen Hawking's involved, that's great. But for me, what impressed me about it is just an exceptional array of young leaders of science who are involved in the actual team doing the work. And we have 2 speakers today who really embody this. One aerospace engineer and one astrophysicist. Dr. Zach Manchester and Dr. Blakesley Burkhart. So Zach is a postdoc down the road at the Agile Robotics Lab. He formerly worked at NASA Ames, where he worked on CubeSats. He joined us from Cornell, where in his PhD, he pioneered the development of the tiniest ever satellites, the centimeter scale sprites, little circuit boards. And over 100 of these sprites, a few grams each, are launched inside a CubeSat, which Zach's also one of the first people to finance a space mission on Kickstarter. I think NanoSatisfy beat you, right? Were they Arduino were the first?
ArduSat flew before me, but theirs didn't work.
Okay. And neither did, well, all right.
Mine worked more than theirs did.
Okay.
There's no deal with it.
Right. So Zach is now working on among things, agile aircraft, and I went to deal. So Zach's past training also includes playing bass for a band called the Strange Attractors, which I think is a wonderful band name, and he's keeping his hand in the space game as part of the Breakthrough Starshot team. With him is Blakesley Burkhart, who's a postdoctoral researcher here at the Center for Astrophysics, and she's simultaneously an ITC fellow, a submillimeter array postdoctoral fellow, and an Einstein postdoctoral fellow. So that must keep her busy. Blakesley joined us in 2014 after completing her doctorate at University of Wisconsin-Madison. Her main research is on magnetohydrodynamic turbulence at all scales, from the solar wind to the interstellar medium to the gas between the galaxies. So she takes, let's look at the messiest thing that happens, which is turbulence, hardest to understand, right? And then let's add magnetic fields to make it even worse. So I'm just intimidated. But not only that, Blakesley is also a motorcyclist, a scuba diver, and a podcaster. And I just discovered from reading your website that you're also a Latinist. So Dabis auditorio in linguam Latinum. So a really impressive team from Breakthrough Starshot representatives, Zach and Blakesley. Please welcome them to hear about this project. Thank you.
We are here. This is home. But for most of our history, we knew only our cradle in the corner. We awakened on this tiny world beneath the blanket of stars, without a note to explain where we come from, who we are. We inhabited a tiny universe, oblivious to the rest of the cosmos. It was only 4 centuries ago that we began to use science to reveal nature's secrets and her laws. What is science? It's an epic journey of discovery. It's a continuity of minds. It's standing on the shoulders of the giants who came before us, looking out across a valley, over a hill, up to the sky, and asking, I wonder what's there.
Oh, that view is tremendous.
It allowed us to look across space and time, see the scale of the universe, and our place in it. We now know that our galaxy alone holds hundreds of billions of stars, and that the visible universe contains at least 100 billion galaxies. In the last decade, we have discovered over 2,000 planets beyond our solar system. It's now estimated that there are tens of billions of habitable planets in our galaxy alone. Are we content to gaze at all these stars, all these worlds, from afar? We have taken to the sky. We have stepped off the Earth. We have walked on the moon. We have landed on planets and comets and ventured to the edge of deep space. Where now?
So good evening, everybody. Tonight, we would like to have a discussion about the question, can we visit the stars? As Jonathan told us, this is a very difficult thing to do. The distances are extremely vast, and the question we'd like to hopefully convince you of tonight is that it's now possible with current technology to visit our nearest stellar neighbors. But first, I'd like to convince you also that this is difficult, right? Why haven't we done this yet? Why haven't we visited our nearest neighbors? Well, to quote Douglas Adams, space is big. It's really big. Tonight, we have all of you all in the room. We also have some viewers around the world, and probably some of these viewers might even be joining us from the other end of the Earth. That's just peanuts compared to space. On this plot here, I'm showing a scaled down version of our solar system all the way out to our nearest stellar neighbor, Alpha Centauri, the Centauri system. The numbers here from the sun to the Earth, right? So this 1 here represents 1 astronomical unit. That's about 93 million miles. And so from the sun out to Earth, Earth to Saturn, that's 10 times that. And then out to around the edge of the solar system, a little bit past Pluto, we have 100 times the Earth-Sun distance. So these are now factors of 10 going out, okay? So this is a very, very large distance. We're talking 1 million times the distance between the sun and the Earth. That's still hard to wrap our head around, right, in terms of these big distances. So I'd like to scale it down even further. So now I'd like you to imagine that this 93 million mile distance between the sun and the Earth is an inch. Okay, so this is now an inch, so kind of measure it out of your finger. This is the sun and the Earth. This distance from the sun out to our nearest star would be 4 miles. Okay, so picture 4 miles in your head and an inch in your hand, right? That's the relative distance we're talking about. Another, I kind of think, nice example, which I'll need maybe 2 volunteers for. Yes? Excellent. That was easy. You can be the sun. And who is my other volunteer? Okay. This is Proxima Centauri, slightly reddish star. And maybe someone in the back can stand up. Great, thank you. So we have the sun here, and you're the Earth. But in fact, you're a lot smaller. The Earth, in terms of the scaled down version, would be a grain of sand. So I hope you brought your grain of sand. You can hold it up. Yes. So this is the relative size and distance of the sun and the Earth. Now you're out here. You're at the Proxima Centauri, Alpha Centauri system. Do you have an idea of where you should go? Do you like Miami? It's about 1,400 miles away. Yeah, we'll get you a ticket later. Thank you, guys. Thank you. So this is the relative distance we're talking about. It's enormous, right? How are we going to get there? Well, we could go on foot. Okay, so this is about as fast as I walk. It's not too fast. This is about 42,000 kilometers in a year if you just keep walking. It'll take about 1 billion years to get to Alpha Centauri. All right. Well, we can do better nowadays, right? We've got cars, we've got airplanes, and we even have spacecraft, right? So the Voyager spacecraft that Jonathan told us about has actually already exited our solar system, is now in interstellar space. Even with these faster forms of travel, it will still take millions or even tens of thousands of years with our fastest possible spacecraft, Voyager, and New Horizons, to traverse this distance to the nearest star. This is a big problem. We're not there yet. But what if we could use light? If we could travel at the speed of light on a light beam, then we would get there in about a little more than 4 years, right? So even the very fastest possible speed limit, light, will still take 4 years to get there. Okay, so how are we doing? So here's our sort of speed report card for humanity. And we're starting out with the steam engine in the 1800s and extrapolating up to today. And so on this plot here, I'm showing speed on the y-axis and units of fraction of the speed of light. And here on the x-axis, the year, right? So 1800, the locomotive, up to 2017. And we've made substantial progress here, right? Like we're talking factors of 10, orders of magnitude of progress over the years. For going from trains to planes to cars and eventually to rockets. Of course, these points here are currently at the fastest is the Voyager and New Horizons, which just flew by Pluto a few years ago. Our proposed mission called Starshot would be a significant leap again. So this is good news, actually, right? So if we look kind of at a cartoon version of this, we can see that roughly every 50 years since the locomotive and since cars, we've been getting about 100 to 1,000 times faster speeds. And so if we keep extrapolating this trend, then we might have some hope of, in fact, reaching the stars. We still have a problem, though. Right now, our current technology in terms of rocketry is based on using a chemical propellant and basically firing that propellant out the back end of the rocket to produce thrust. And the equation that governs your maximum achievable velocity is called the rocket equation. And so I won't spend too much time talking about the details of this equation, but essentially the maximum speed that your rocket can get is proportional to the exhaust speed of your propellant times this factor of the ratio of the initial to final mass, right? And that's because when you have a rocket with propellant, chemical propellant, you have to carry that mass with you, right? You have to carry your propellant with you as you accelerate to achieve your final velocity. So this is sometimes called the tyranny of the rocket equation, is because this term is logarithmic. So it's really strongly dependent on the mass of the fuel. To put this in sort of a pictorial version or a plot version, we've got speed on the x-axis here in percent of the speed of light. Okay, so this is quite small speeds that we're able to achieve down here. And this is mass of our propellant in kilograms. This here is the mass of the known universe, so roughly 10 to the 55 grams. And so if we extrapolate that out, we're only going to be able to achieve with the rocket equation 0.12% the speed of light. Okay, so that's just simply not going to cut it. That chemical rockets will not get us to the nearest star. Really, to do this in a human lifetime, right, in our lifetimes, we're going to need something like 10 to 20% the speed of light to do this quickly. So we need to rethink our propulsion strategies. And so this is actually what our group at Harvard has been doing over the last few years, led by Professor Avi Loeb. And I've put pictures of our group members and our names down here. It's a group composed primarily of postdocs and students. And over the last few years, and even before Starshot became Starshot, what were we doing? We were reviewing proposals and talking about propulsion methods beyond chemical conventional rockets. So we reviewed a lot of proposals submitted to the Breakthrough Foundation. These included proposals that included nuclear and radioactive propellants and fuel, and those can do significantly better often than chemical rockets, but you're still limited to this rocket equation, and that's because you're taking your fuel with you. Anytime you have to take the fuel with you, you have to obey that equation. And so this also is not going to cut it. Fusion could be interesting, right, to have a sort of a fusion propellant, and with fusion, you could get to something like the 10th of the speed of light. But we don't have fusion yet. We don't have break-even fusion, right? And so this, at the current time, is not possible. Similar with antimatter drives, and there's a number of different proposals for antimatter drive. You can go on Google and read about some of those, and they're all, some of them actually sound quite exciting, but again, we don't really have a good way to store antimatter, to produce antimatter. It's just not possible right now. And then finally, there's the idea of the light sail. And this is an interesting idea in that you don't have to take the propellant with you, right? You don't have to take your fuel with you. And with photon momentum, you can reach roughly the speed of light. So I should also mention that this project has been primarily fueled by pizza. So you can thank Gary Milner for all the free pizza, that we came to this sort of systematic conclusion that light sails would be the best possible solution. And that's the one that that Zach and I would like to tell you about today. So light sails, what's the big advantage? Well, they allow us primarily to leave the fuel behind and to also use a propellant, light, that has a final velocity of the speed of light, right? And so one can actually achieve relativistic speeds without needing to carry propulsion. This is without having to carry the propellant. This is not a new idea, right? And so here's a quote from Galileo in the 1610. He was writing a letter to Kepler. He said, "With ships or sails built for heavenly breezes, some will venture into that great vastness." Right? So he had already started thinking of sailing through the cosmos well before we ever even thought of stepping off Earth. There were a number of papers in the early 20th century, written by several different groups, exploring the idea of using either the photons from the sun for propulsion, or in the 60s when lasers were invented, a number of papers came out talking about using laser power to propel light sails. And this is actually something that's already been tried. This is not a crazy idea at all. In fact, the Japanese Space Agency has a solar cell, Icaros, which has already been launched, tested, and has had a flyby mission by Venus. And so this concept of using the radiation pressure from the sun to propel a spacecraft is actually quite a viable one.
When was that done?
This was very recently, just a few years ago, the flyby mission to Venus happened. So no one has actually had a space mission or a propulsion mission using lasers, but this is something that, as I said, has had a lot of papers published on it, including schemes such as this one by Robert Forward, which are very similar, if you read the abstract, to our current proposal for the Starshot mission. So why all this excitement about laser light sailing? Well, as I said, it doesn't have to obey this tyrannical rocket equation because we don't have to carry the fuel with us. And so how then does the speed scale with all the parameters involved? So the final speed is dependent primarily on the power of the laser array, the array size, so your laser array size, the wavelength, and then the mass of the craft. So those are the main components of the sort of final speed that you can expect to achieve. So it has a weak scaling with payload mass, so that's good, although it still depends on it, of course. Now, if I think about my laser pointer here, if I plug in all the parameters of my laser pointer, I can accelerate about 1 gram of mass to the speed of an ant in a week. Okay, so this is a pretty dinky little laser, but hey, I can still make it propel some sort of payload. So that's something. Now, we want to do a little bit better than the speed of an ant, right? We want to get to relativistic speeds. And so launching 1 gram, so the same sort of mass of this laser in terms of the speed of an ant, launching 1 gram to 20% the speed of light might require something like 50 gigawatt laser power, and will ultimately, over 2 minutes, be an energy level comparable to the launch of the space shuttle. So something on the order of 10 terajoules. So we're talking about a big laser array with a lot of power in order to achieve this. So on the surface, it sounds quite impossible. But in fact, in 2017, with current technology, there's three facts that made us think, gee, this is actually now something that's achievable. One is the miniaturization of electronics, right? Does anyone have a smartphone or an Apple Watch? Right? So actually the guts of your smartphone weigh on order of a few grams, right? The Apple Watch chip is roughly the same size as the star chip that Zach will tell you about shortly. So this has already happened now. We can put a lot of instrumentation, communications devices, cameras, etc., on a very, very small platform. Another thing is that material science and nanotechnology have advanced a lot, right? So metamaterials can be extremely lightweight, and we can have a sail thickness now of order of a few atoms thick. And so this means that our sail could now be extremely lightweight and extremely durable material. And finally, number 3, everyone's favorite, lasers, right? Laser technology has really come into its own in the last couple decades, and this has driven the cost of lasers down in an incredible way, almost a Moore's law exponential a type of driving of the cost of lasers. And so now we can build a laser array of a large size at a sort of inefficient or inexpensive sort of cost. So this has excited a number of people that actually want to see this through, including people with money. So Yuri Milner, pictured here, and Mark Zuckerberg are on the board of the Breakthrough Foundation and the Breakthrough Starshot, as well as Stephen Hawking. And there was a press release last year describing this project and how it is now currently possible to achieve. And with that, I'll turn you over to Zach, who will tell you a little bit more about the engineering aspects of the project.
I'm going to just restart this video for a sec. Let's see if I can make that work. Okay, so this video kind of gives a high-level sort of artist conception of the game plan. So the idea is that we're going to build a bunch of these tiny spacecraft attached to sails, launch them into Earth orbit in a rocket. We're going to deploy them out in Earth orbit, and then we're going to shoot these things with a really, really big ground-based laser for a couple of minutes. So the power in that laser is something like 100 gigawatts, which is a lot, obviously. And so the idea here is, right, we shoot this laser at the sail, and over the course of a couple of minutes, accelerate it to about 20% the speed of light. And off it goes. So after that couple of minutes, it's just coasting, flying out there. And if all goes according to plan, roughly 20 years later, it'll sort of fly by the Alpha Centauri system. And the flyby actually will last something like a couple of hours. The actual amount of time it spends in the Alpha Centauri system is going to be on the order of an hour or two. And the goal of all of this is to be able to get pictures like this, and other science data as well, but of these sort of pictures of Alpha Centauri, of any exoplanets around it, and send them back to us. So to put this in perspective too, 20 years to get there, we're 4 light years away. The data is coming back in a signal that's traveling at the speed of light. It takes 4 years just for that signal to get back to Earth for us to get those pictures back. So the whole thing is something like a 25-year mission after it's launched. Okay, so that's the game plan. Who thinks that sounds doable? So here's some of the really big challenges associated with pulling this off. The first one is maybe the most obvious. How do we build a laser that big? So not only is the power involved enormous, to put that in perspective, that amount of power, or the amount of energy, right, in that shot over 2 minutes is about what a commercial power plant puts out in a full day. So if you took a commercial power plant that powers a city and just saved up all the energy produced for 24 hours and released it in 2 minutes into this laser, that's how much power we're talking about. So that's extreme. In addition to that, the laser has to be physically really big, and there's sort of physics reasons for that. But it needs to be about 1 kilometer across in order for it to be able to focus down to a spot the size of the sail out in space. So basically, the bigger the laser is, the tighter focus you can make the spot. So in order to make this all work, in order to get the spot down to a couple meters to the size of the sail out in space, we need the laser to actually be 1 kilometer across. So that's challenging. So the next thing that comes to mind, right, is we're shooting this enormous amount of power into this focused spot on the sail. How do we make sure the sail doesn't just cook? How do we not vaporize the sail, right? So that's hard. Another one that's one that I've been particularly interested in for the past year is how do we actually keep the sail on the laser beam? So you can imagine, this is sort of analogous to, say, like blowing on a sheet of paper in this picture, right, with a flat sail. How does it not just blow off the beam? How do we actually keep it on there for that 2 minutes without flying off? That's an interesting problem. And then the next one is how do we build this, the electronics and all these subsystems that need to go into a satellite? How do we shrink these down into a sort of gram scale package? That's something I've spent a lot of time on as well. And then the last one is, once we get there, how do we get this data back? No one's ever closed a communications link over 4 light years. How do we even do that, right? As an engineering challenge, that's also pretty tremendous. So I'm going to talk a little bit about each one of these and kind of where the state of the art is now and where we're going to need to take it in order to make this happen. So first off, the laser arrays. So this is an example of a phased array laser system. So what that means is, so we're not going to be able to build one laser that's 1 kilometer across, right? So obviously what we're going to have to do is build a bunch of small lasers and somehow add them together, right? Spread them out over this kilometer aperture and add the beams together. So in order to add those beams together, they have to be phased. So what that means is, if you remember how kind of waves add and they have like kind of peaks and troughs, you need to make all the peaks line up so that they add together without interfering and canceling out, right? So in order to do that, when you put a whole bunch of transmitters together and line everything up like that, that's called a phased array because you're lining the phases up. That's been done in radio for decades, and it's pretty easy to do in radio because the wavelengths are nice and long. So radar, for example, typically the wavelengths are sort of roughly a foot. So you have to line these things up to within a fraction of a foot. When you go into optical, though, and we're talking about a laser, the wavelength on the laser beam is a micron. So that means we have to line these beams up to within a fraction of a micron. So it gets way, way harder to do. This has only been done recently within the last 10 years or so that we've actually been able to build phased arrays in optical bands like this. So this is an example of one. This is 19 lasers put together in a really precisely machined kind of housing, and that's built in a lab. So this has been done in the lab setting on the order of, say, dozens of lasers. We're going to need to be able to scale this up to kilometer across and thousands, maybe even tens of thousands of individual lasers. So that's really hard. I would say, though, the fundamentals are well understood. We know kind of how the physics works. We've built these kind of lab scale systems like this. It's a matter of scale and mass production, I think. Maybe even the hardest part of this is just going to be building enough lasers to do this on a production scale that's economically viable without the cost being sort of astronomical, pardon the pun. Okay, so that's the laser system. So on the business end of this laser, we have a sail, right? And this gets to how do we make a sail that doesn't just vaporize under this much power. So this is where there's been a lot of progress in the last 10 years or so. This is an area called metamaterials. Has anyone heard of metamaterials in the room? Okay, so a couple of people. So what's going on here, this is actually work that's been done at Harvard down the street by Marco Loncar's group. They build what are, I think, probably the world's shiniest mirrors. So the way they do this is a thin sheet of diamond, and they actually micro machine these little golf tee looking things into the surface of the diamond. And what they're doing, these little golf tees are a fraction of a wavelength in size. So if you can build features into the surface of a material that are kind of sub-wavelength in scale, what they've actually done here is build these little resonant cavities. So this surface features on here actually are smaller than the wavelength of the light. And as the light comes in and bounces off these things, it creates an interference pattern. And you can actually build basically perfect mirrors this way. Almost as close as you can imagine getting to perfect. by building in these little tiny sub-wavelength features. So this is what it looks like. And to put this is current technology. We can do this now. This is that diamond micro machine mirror on the left. And these are kind of the best existing sort of standard, what are called dielectric mirrors. This is a very high-end version of like your bathroom mirror that are used in laser applications, these other two. And this just shows how much power they can take without damage. So you see if you pump enough laser power, this is megawatts on the left, into these standard mirrors, they eventually, they're damaged, they kind of get cooked, right? But in these tests, this diamond mirror withstood 225 megawatts. That's megawatts per centimeter squared. So that's actually a factor of about 100 better than what we need for Starshot. We're talking about 100 gigawatts, but it's spread out over a few meters, a few square meters area. So that's actually better than what we need. And basically, they didn't have a big enough laser to destroy this material. They pumped as much power as they could into it, and it survived just fine. So there are materials on the horizon that can actually withstand this kind of power. The one gotcha, the one caveat with this stuff is because they work by these kind of really fine structures that are kind of engraved into the surface, the orientation matters. So that mirror only works this well when the light comes in at a perfect 90-degree angle. If you tilt the mirror, that reflectivity drops off and it starts to absorb. So that's kind of a caveat, right? But there is a lot of promising stuff going on in this area right now. There's actually research right now in expanding sort of what they call the acceptance angle on these materials and making them able to handle light coming in at angles other than dead on and still work okay. So I would say we're actually in the ballpark with these materials that are out there today. The big thing I think is going to be making them able to work at a wider range of angles and to make them light so that we can actually build this spacecraft at a low mass. Okay, so here's some stuff that I've worked on a bunch lately that I think is super interesting. So this is kind of a frame out of that video showing this, kind of artist conception sail laser beam setup. And this is a flat sail, right? So who thinks a flat sail is stable? Who thinks that's going to stay on the laser? Okay, so this is just for fun. So I think a good analogy for this situation is like trying to shoot this piece of paper up at the ceiling or hover it by blowing on it. So does anyone want to give this a shot? Who thinks they can do it? Go ahead. All right. So do you think you can make that, hover over your head without flying off?
Probably not. But I can try.
Give it a try. See what happens. You have to let go.
I was trying to stabilize it and make it straight and then let it go.
So spoiler alert, it's not possible. So so the people who made this video, they're really nice graphic design artists maybe, but they're not engineers. So yeah, this doesn't quite work out. So I spent a bunch of time thinking about this and looking into ways to make it work. One thing that kind of works, this has been proposed in the literature. This is kind of what people had nominally in their heads going into Starshot, some of the people involved. So the idea is you make a cone. You make the sail shape like a cone. And you can imagine that if you center that cone on the beam, if you move off the center a little bit, it'll kind of reflect light in the kind of opposite direction and push you back towards the center because of that conical shape. Unfortunately, what also happens if you move off the center is that the cone starts to flip over. So it doesn't quite work. So it turns out you can make it work if you hang a long pendulum off of it to kind of counteract that torque. So this is what people were talking about when I first got involved in Starshot, and it seemed a little crazy to me for a couple of reasons. So the cone thing seems okay, but a big problem with this pendulum thing is, one, the assumption is that this pendulum is rigid, that it's not like a string dangling down there, that's actually attached by some kind of like rigid pole to the beam, right? So this whole thing has to be stiff and rigid, and that's going to be really heavy. The other thing is that pendulum's hanging out in the middle of the beam, in that laser beam, right? So that maybe is problematic. There might be some thermal issues there. So this is one, but this is a nominal architecture that could work from a stability standpoint. I think there's other issues with it, but that's a maybe. So another option that I came up with recently with Avi Loeb here is turning the sail into a sphere. If you make imagine inflating like a giant shiny ping pong ball, So if you think about it a little bit, if you have like a single ray coming up, if you have a single beam, that's not stable, right? You can kind of look at the picture here and imagine the way that reflects off, and if you move a little off the center, it's going to get pushed off. But if you make the beam yourself, if you can turn some knobs on the laser and shape the beam, you can actually make this stable. And here's an example of a beam shape that works. So the key here is, instead of having kind of a unimodal beam, a beam with a single big peak in the middle, if you can hollow the beam out, if you can basically reduce the power in the middle and put more power in the sides, now you've got this kind of nice little bowl there, and that giant ping pong ball will kind of hang out in the middle of the beam in that bowl. And if it moves off a little bit, the power in the side lobes will push it back. So you can actually make a stable sail this way too. So that was kind of interesting. Okay, so that's some ideas on kind of sail stability, sail materials. Now onto the kind of spacecraft end of things and the electronic stuff. So this is what I spent my PhD on. I have a couple of these to pass out for you guys, of course. So we got one that can go around this side. And I know there's people in other rooms, unfortunately, who don't get to see these. So if you can come up after the talk. If someone wants to catch up there, I can throw you one. Yeah? It's okay. They're durable. Somebody want to catch one up here? Yeah? It's a little far. Let's see. Okay. Okay, so what's on these guys? These are about 3.5 by 3.5 centimeters. They weigh about 4 grams. And they have kind of all of your traditional spacecraft subsystems on a single little circuit board. So there's a solar panel, there's a little computer on there, there's a radio, and there's some sensors. So we have on here a 3-axis gyroscope, which measures rotation rate, and a 3-axis magnetometer, which measures magnetic field, like a compass, basically. And yeah, I spent a bunch of years working on these during my PhD and built a bunch of them and tried to fly them in space a few times with some mixed success, as Jonathan alluded to. And yeah, so the idea here is we can actually fly these things in low Earth orbit and get signals back from them on the ground. These are little tiny satellites. So so this is kind of, I think, this is still probably a couple of orders of magnitude off from the capabilities we need for Starshot, but it's a start. These are, I think notably, these are in the ballpark on the mass number to which you need, right? So we can build gram-scale spacecraft now. So this is some of the things we did with these. This was a mission that we were very lucky to get involved in 2011. This was the second to last space shuttle flight that a few of these went up on. So this is an earlier sort of prototype of the boards that I handed out. This is the 2011 model. The ones you have are like the 2014 model. So so we got a chance to put these on a Naval Research Lab's materials science experiment called MISSY-8 that went up to the space station. And this is a picture of it getting installed. So this is a picture taken out the window of the ISS, out the cupola, if you know about the ISS. I love these pictures. So this is an astronaut taking a picture out the window of these two astronauts on a spacewalk installing this thing. I'll try to behave and use this. So if you look carefully, this astronaut's actually holding a camera, taking another picture. So here's that picture, and then here's the other astronaut taking a picture after the experiment was installed. So this is the actual experiment. This is MISSY-8. It was actually, I kind of mentioned, it was a materials science experiment. So they had samples of all kinds of exotic, special engineered materials, and they basically put them outside the space station, out in space, to see how they held up to the space environment, to see how they survived. And here's the last picture. So here's our little boards hanging out in space right after they were installed by these two astronauts. They actually spent about 3 years on orbit, on just sitting out there in space like this. Unfortunately, we weren't able to get any radio signals back from them for it's not too obvious from these pictures, but Earth is this way. And these were kind of hanging out on what's called the anti-nadir side of the space station, facing away from us out into space with a big hunk of metal space station in the way. So we couldn't get any radio signals from them. But they hung out up there in space for 3 years, and we got them back at the end of 2014. Here's what they looked like when they came back. A little worse for wear. But we actually got these and put them under a lamp in the lab as soon as we got them back, and they powered right up and started transmitting. So they work. They survived 3 years in space, all the radiation, the whole deal, and they worked when we got them back. So that's a nice data point to have. So fast forward a couple of years, and this is some of what Jonathan was talking about during the introduction. This is the kind of next step in this line of work. We decided we wanted to actually fly these things as free-flying satellites. So we built this kind of mothership satellite. So this mission was called KickSat for kind of obvious reasons there. And that mothership satellite's about shoebox size. And it holds about 100 of these little tiny chip satellites inside it. And we get that mothership satellite launched on, so this flew once, and we're actually working on getting it flown again. We're doing a KickSat 2 right now. But basically, this mothership satellite goes up on a rocket and gets deployed in low Earth orbit. And after a few days, we send a signal from the ground station and trigger this deployment. And these guys all get flung out into space. And then we try to talk to them and get data back and all that good stuff. So this was the artist's view, and then this is the actual test of this thing. This was back in December, actually. This is KickSat 2. This is the sequel. This is us in the lab trying to do a little test. As you can tell, my catching skills maybe need a little work. These are two undergrads, actually, back at Cornell who've helped me out with this a whole bunch over the years. So I'll play it one more time because it's fun. So what's going on here? This is an antenna deployment. So you see these little antenna, like kind of bunny ear antennas pop out. Those are the communications antennas for the mothership, actually. And then this is the Sprite deployment. So that's a little fast. But basically, there's a big spring-loaded, kind of mechanism in there, and it's all tied down with actually it's screwed down with a nylon screw, and then there's a what's called a burn wire in there. It's basically toaster oven filament wrapped around the nylon screw, and we run current through it and melt through the screw, and that's what triggers the whole thing. So that's kind of fun. Okay, so this is basically, this is my PhD. That was fun. So last step, I want to talk a little bit about that communications problem, right? So we've got the tiny satellites. We can talk to them from low Earth orbit. We use radio for that. But what happens when you get really far away, right? So let's think about it from this perspective of we have a tiny satellite. We only have so much power available on that satellite, right? So as we get farther away, we can't keep jacking up the power that we're transmitting with. We're also only so big, so we can't just keep making the antenna bigger and bigger. So what happens as we get farther and farther away? How do we deal with this distance, right? How do we close that communications link? So one thing you can do is, all right, so this is kind of how the beam coming out of an antenna looks. This theta is an angle. So this is the angle of that beam, how far it's spread out. And it's mostly a function of these two numbers here. So this lambda up top is the wavelength of the signal. So this, if it's light, it's really short, like microns. If it's radio, it's maybe centimeters or meters. And this d is the diameter of the transmitter antenna, like the dish. Okay. So let's say we have our Starshot satellite. This d is maybe a couple meters. That's all we've got, though. We can't make that any bigger. And we want to focus this power down really narrow. So what can we do? Who has any suggestions? We can't make that any bigger. We can do something about this, though, right? So we want to make that wavelength really tiny, right, in order to make this angle really small so we can focus that beam in really, really tight. So it turns out, if you want to go smaller and smaller wavelengths, you go from radio waves, you get really, really tiny, you get to, terahertz, you get to millimeter waves, and you keep going, you get to optical. You get now to visual light, and you get really short, right? So if we're in the kind of micron range, this becomes a laser. And this is optical communications with lasers, which is actually a thing now as of a couple of years ago. And it's actually been flown on spacecraft missions. So this is the LADEE mission. This actually flew out of NASA Ames when I was working there in, I think, 2013. You probably know. Did I get that right? Yeah? Okay. So this flew around the moon with this thing called the LLCD on it. This is the Lunar Laser Communications Demonstration, I think is what that stands for. This is a zoomed-in picture of this thing. So this was an optical communications demo done from the moon back to the Earth with a laser. So this thing had a laser with about a 10-centimeter aperture. This is the aperture. This is kind of the telescope attached to that laser. Half a watt laser. So pretty reasonable in terms of power, just half a watt. And shoot this back to Earth, and the receiver on the ground that they used to pick this up was a 17-inch telescope. So a telescope about that big around, not even very big, right? and they set a record for the highest communications data rate ever achieved from space. So they got to 622 megabits per second this way. So this wasn't even, this was a small receiver, a small transmitter, no huge dishes, right? And it's because they were going really, really tiny with that wavelength. So so imagine what you could do if you built a really big ground station receiver, right? What if you used a really big telescope? And it turns out if you run the numbers on this, if you look at that 4 light-year distance and you look at something like this, some optical system, and you take the biggest ground-based telescopes we have right now today and try to close a communications link, you can actually do it at about 20, 30 bits per second with something like this. So it's actually doable. If you could have this size aperture, a watt or two of power, and like a 20-meter-ish telescope on the ground, you can get tens of bits per second. So it's doable. It's really hard, though. And if we want to send pictures, right, we're going to need something better than that. So I think what it ultimately comes down to is we're not really going to be able to squeeze any more power out on the spacecraft side or make a bigger transmitter on the spacecraft side. We're going to have to make the ground station bigger. We're going to need really big telescopes on the ground to make that data rate higher to get pictures back. Okay, so I guess this is just kind of the summary slide. This is all the stuff I talked about at the beginning of that video, but anyone have any questions on this stuff? I guess what I want to emphasize is that this is about 2 minutes. This is about 1 kilometer. This is 20 years. This is an hour. And then this takes another 4 years to get it back. This is just kind of the scaling. Oh yeah. So we're going to wait for the end. Sorry, I'm misbehaving. Okay, I guess you're up again.
So we'll definitely have time for questions, but before you hold on to your questions about all the engineering and the stuff I talked about before that, I actually want to excite you guys just a bit more and talk about science. What will we learn out there if we actually realize the Starshot program? And hopefully Zach convinced you all that the engineering is certainly possible even with today's technology. What will we find? And if we look at our kind of nearest neighbors, so the sun here, at the edge of the solar system, the Oort cloud, 2 light years out, 4 light years out, we have the Proxima Centauri system, and then roughly 6 light years or so out, we have a few other stars which we could visit. And so that would be already something that would be achievable with the Starshot program. Now, in terms of places to go and things to see, well, it would be really cool to actually visit some potentially habitable Earth-like planets. And the Kepler satellite has informed us that about 20% of the stars in our local neighborhood may indeed have Earth-like planets. And this picture here, this plot is showing you the temperature of the stars. So Sun-like star being roughly at this temperature here, sorry, at 6,000 Kelvin, Venus, Earth, and Mars up here. And then the incident starlight that the planet receives relative to starlight on Earth. So again, Earth is right here. It's in the habitable zone, which is the sort of sweet spot to host liquid water. And then there's a number of worlds outside of our solar system that could potentially be candidates for planets that have water. And so these would be really cool places to visit. The goal of the Starshot mission, there are many scientifically interesting things to do, of course, but the goal is actually to visit Alpha Centauri within our lifetime. So we're thinking 10 to 20% the speed of light, final velocities, which at 20% the speed of light should get us to the Alpha Centauri system in about 20 years or so. This is a fly-through of the Alpha Centauri system. In fact, the Alpha Centauri system is not just 1 star, it's 3 stars, right? So we get 3 for the price of 1 here. There's Alpha Centauri A and B, which are in fact sun-like stars. And could have planets. They're a binary system, so they're orbiting each other. They could have planets out to about 30 times the Earth-Sun distance, so 30 AU orbiting those stars. We haven't discovered any planets around Alpha Centauri A and B, but it's certainly possible that stable orbits exist there. There's a third star, Alpha Centauri C, or Proxima Centauri. This is a red dwarf star, and it's actually our closest star. So this is the first target of Starshot. And the really exciting thing about this particular science target is that Alpha Centauri C or Proxima Centauri star has a Earth-like planet around it, Proxima b, which is in the potentially habitable zone, so the zone that could have liquid water around its host star. And so this discovery was reported just last year, 2016, that Proxima Centauri C has this Earth-like planet. It's very close into the star. The star is very cool. It's a red dwarf, and so it has a very small orbit. About 11 days is 1 year on this planet. So you could have a birthday party every 11 days. So that's exciting. The star is a very cool star, and so the primary wavelength, the peak wavelength, is in the infrared. So if someone is living on Proxima b, then they might have infrared eyes instead of optical eyes, like our eyes are geared for. And there's just a lot of questions about what's happening in terms of the habitability of Proxima b. And so there's a lot of active research, active literature being written about this particular planet. So it will take about 20 years to get there. And then, as Zach mentioned, 4 years to send any sort of data back. But there's plenty of interesting science that we could do along the way. In particular, I'm very interested in the nature of the interstellar medium. Space is, in fact, not empty. There is gas, dust, magnetic fields permeating the interstellar medium, the space between the stars. And this is actually, we're now making in situ measurements of the interstellar medium with the Voyager spacecraft. And potentially we can do this as well with the Starshot mission to actually probe and measure the gas and dust and the plasma within the interstellar medium. Another extremely exciting aspect of the Starshot mission that I'd like you all to keep in mind is that it would be a completely new paradigm for the exploration of our own solar system. If you think about the way our solar system has been explored by NASA and other worldwide space agencies thus far, we spend a lot of money, billions of dollars, on single missions with a very narrow goal in mind, and that's because it's extremely expensive to launch missions to other planets in our solar system. But with Starshot, we'll be able to launch multiple spacecraft with the laser array, and we'll be able to achieve speeds that mean we can visit planets in our solar system, moons in our solar system, on the order of days or weeks rather than years. So, for example, the New Horizons mission, which just visited and flew by Pluto a few years ago, this took 9.5 years from launch to arrival at Pluto. And with Starshot, at the speeds we're considering, this would take on order of a few days, right? And so this would open up a huge new way for studying the solar system and planets and moons. And one other thing that could be extremely interesting and even critical for the Starshot mission to succeed is the composition of this interstellar and interplanetary medium. And that's because the Starshot mission, the starred ship, as it's flying through the interstellar medium, it will interact with gas and dust along its path. And if it hits a large dust grain on the starship or the spacecraft, the dust grain traveling at these sorts of velocities will create a hole or a crater, which will also melt part of the starship. And so we recently published a paper considering the expected amount of hydrogen, helium, up to iron in the interstellar medium between us and Alpha Centauri and Proxima Centauri, as well as the dust distribution. And this will be a big problem for Starshot. Basically, it will encounter a lot of the dust and gas along the line of sight towards Alpha Centauri, which will erode the spacecraft. And so it has to have some sort of protective shielding in order to deal with that problem. Of course, there's other challenges, right? Zach already mentioned a few of them, and here's a list. If you go to the website for Starshot, breakthroughinitiatives.org, there's a challenges webpage with a blog that you can go on and read about a lot of the challenges that Starshot will face. In particular, the laser array, the sail stability and the sail integrity, collisions from dust that I just talked about, launch, etc. So these are all challenges, but I'd like to really leave you all not with the challenges, but with the exciting aspects of Starshot. This is what Earth and the Sun will look like from Alpha Centauri. So this is looking back towards Earth, right when we're sending all the data that we'll be able to get. We're actually in the constellation of Cassiopeia, which we might be able to see tonight because the skies are very clear, so that's exciting. But when we look back from Alpha Centauri, this is the view that we'll have. At the moment, where we are now, this is where we'd like to be, is that through the generous donations of the Breakthrough Foundation, Yuri Milner, Mark Zuckerberg, and other donors, they've offered up $100 million for the research and development of the Starshot program. And there will be calls for proposals and ideas. It's an open project, so you can go onto the website. You can read about the challenges and the discussions there. And it's very much invited to take part in this epic journey. So now we'll take your questions, and thank you very much for your attention.
Okay, who's up first? I think.
So this is going to take 25 years, and it's going to take a lot of money. The alternative would be in 25 years, for a lot of money, we will have extremely good telescopes. What do we need this mission for?
So you want to talk about this? Do you remember the numbers for this?
Yes, it's actually a great question. It reminds me actually of the situation we have studying the interstellar medium. I look at planetary scientists with envy because they have in situ measurements. They can actually build probes and collect data directly and measure directly what's happening in the solar wind, in the interplanetary medium. They get actual direct data.
From telescopes?
From in situ measurements from spacecraft in the interplanetary medium in our solar system. Now, I study the interstellar medium, so I have to rely on indirect observations from telescopes, which are always limited because I don't have the full 3D picture, right? Because I'm just limited to what we get along our line of sight. It's very difficult to make direct measurements of things like the magnetic field, the velocity of the particles. So there's a lot you can do with telescopes, but it's nowhere near the information scientifically that you will get when you have direct measurements. And so the Starshot mission will open up completely a new way of studying the interstellar medium.
You want me to do that?
Yeah, I feel bad.
Choose to go with someone on the balcony there.
Can you say something about the problem of pointing the laser back? It seems like it has to be pointed really precisely.
It does. That is very tricky. So ultimately what that comes down to is, so I kind of put up that equation, right, with the kind of beam angle. And what it comes down to is you basically only get to make that as small as your pointing accuracy, right? So you can, theoretically you could make that lambda really tiny and that d really big and make it really tight beam. But if you don't have good enough attitude control, if you can't point that finely enough, then your beam's, is totally wasted, right? So there's kind of two pieces to that, and what it really comes down to is you make the attitude control as good as you can, and then that also puts a kind of a bound on the beam width you can have and the amount of gain you can get from the system, right? So it is definitely a factor, and we're going to have to figure out how to do attitude control on a gram scale, very thin and light spacecraft. So that's something I'm actually really interested in, not just for this. I've been thinking a lot about the last couple of years doing attitude control on these sort of gram scale spacecraft that I work on. So I think there are ways to do it, and I think it's a really interesting problem. So if you know anything about how attitude control works on large traditional spacecraft, they use these things called reaction wheels, right? So you have basically a flywheel, and you spin the flywheel, and then the satellite kind of goes the other way, right? And you can't do that on the side scale. It just doesn't happen. So we need to rethink how we do it, and the actuators and all that kind of stuff. So I think it's a really interesting research problem.
There's one at the back.
Do you have any estimate of from production to launch?
How long it's going to take from now to launch it?
From now to created, make it and launch it? Any guesstimate on
The
years?
stated goal of on the project website is 20 years. So
And then
from
we-
now until launch to Alpha Centauri. So there'll be scaling tests at every point along that 20-year time scale. So the final project goal is the 20% the speed of light Alpha Centauri, about a kilometer array. But we can build smaller arrays and sort of scale up. And there's still, I think, interesting, especially solar system exploration, that you could do at lower speeds that can be achieved before the 20-year stated goal timescale.
Although I would say, my understanding is the 100 million is for technology
Oh, yeah.
development.
That's for the
We'll
research
need
and
a lot
development.
more to actually, but so it
Yes.
isn't funded all the way
Yeah.
through. There was someone over here earlier.
In terms of attitude control, you have that if you take pictures as well.
Yeah.
Normally in spacecraft, you have some sort of propellant on board to do that. I don't think you do that.
So actually, you don't. You, typically, so it's a little subtle, but you don't actually generally use propellant for attitude control. You use internal momentum actuators like reaction wheels. So you need propellant to do what's called momentum dumping, but there's other ways to do that. So I mean, I'm happy to talk about this later, but yeah, it's basically you don't want to use propellant for attitude control, and it's not done that way on traditional spacecraft because once you're out of gas, you can't point anymore, right? And these things are designed to last for 10, 15, 20 years sometimes. So the way it's typically done, you can imagine like a flywheel, and it's just equal and opposite reaction. You spin the flywheel one way, and it makes the body of the spacecraft go the other way. So you have 3 of those for X, Y, and Z, more or less, and that's how it works. There's caveats to that, but that's usually how it's done.
We have one over there.
What about mid-course correction capability?
So that's another interesting question. We don't have a good answer for it. So ultimately, it's really hard because if you think like sort of trigonometry, right? If you've got 0.2 c going this way, you want to move that a little bit, you're going to have to put out a significant fraction of your 0.2 times the speed of light to nudge the trajectory over, right? And how do you do it? So we don't necessarily have a good answer for that, and I don't. So I think ultimately we would like to be able to do that. At the same time, there's probably ways around that. So one of the things that's been talked about, once you build this giant laser, you can think about shooting a whole bunch of these things.
Like as a spray.
On their way. Well,
one of them might actually get to where you want to go.
So I think, the idea is we're going to send a whole bunch of these things in the general direction of Alpha Centauri, hundreds, and they'll all collect data and each step back and just kind of get what we get. But I don't think it's going to be really, really tough to put out enough delta V to significantly alter the trajectory.
Works when you're shooting at clay targets.
Yeah, that's what it is. So Julie and then the person.
So what state is the laser, and then what media is laser made out of?
So it's a solid state, like nominally, right? The nominal game plan here is to use like solid state lasers, like are used in the telecommunications industry for sending data down fiber optic cables. The reason for that is that they're mass produced in large quantities, and they're there's economies of scale going on there. They're made by the thousands or millions a year. And the idea is that there's a lot of manufacturing infrastructure for that stuff already out there that hopefully we can exploit. That's the idea. Whether that actually works out in practice, I don't know.
I just buy lots of laser pointers.
Yeah.
The lady in the back.
Do you plan to have it go flying past Alpha Centauri, or use its gravity and come back like a comet?
Yeah, the current plan is that it'll be a flyby mission. So similar to New Horizons, which flew by Pluto and kept going, and the Voyager spacecraft, it's very difficult to slow down. It's potentially possible to do using the photon momentum from the Alpha Centauri A and B stars themselves to slow down. There's been some discussion of that in the literature, but it's a very difficult thing. So right now the current plan is just a flyby mission.
There's one up there.
Pluto is 4 light hours away, correct? Well then, if a probe traveling at a fifth of the speed of light, shouldn't a probe traveling at a fifth of the speed of light reach something 4 light hours away in 5 times 4 equals 20 hours, not 3 days.
Yeah, it depends on the final speed of our system. So if we have, it depends on the final speed, but we're thinking for the final speeds on order of a few days.
Yeah, but if you get to point 2C, he's right.
Right. Yeah. Absolutely.
If you travel at point 2C, do you run into the laws of relativity? Do you have to consider those in how you think about this project in any way?
Yes. For the image, that's actually one thing that's been discussed quite a bit in terms of sending an image back. So if we're flying past at 10 to 20% the speed of light, there will be a slight relativistic correction that'll be needed to, when we send the image back, to take into account the final data analysis.
There's also it's not necessarily relativistic, but there's a lot of Doppler shift involved, as you can imagine, right? And that's important actually during the acceleration phase on the laser. What's happening, we talk about these metamaterial things, those are designed for specific wavelength. So as this thing accelerates and the Doppler shift is continuously changing, right? So the sort of effective wavelength that the sail sees is going to stretch out during that, and that's actually a big challenge. So it means you have to not only get these metamaterials to work over a wider angle of incidence, but over a wider wavelength range than they currently work.
Anybody had a question?
Yes, so you would need motors to align the laser towards a telescope. So where do you get the power for the motors? And even if you put solar panels on the outside, won't they burn up from the speed?
So that's a good question. Where
Are you talking about the sail or the laser array?
The sail.
Yeah. So there's.
So I can take that. Yeah. So in terms of the sail on the cruise, I'm talking about the cruise. So this last couple slides I showed on the interaction with the interstellar medium. So while the sail collides with the interstellar medium, there'll actually be an effect that will heat the sail on one side through collisional heating. And that will create a temperature difference between the side that's interacting with the interstellar medium and the side that isn't. So that could potentially be used as a battery of sorts. We can actually get temperatures of up to around 300 Kelvin or so, depending on the density and the speed of the density of the interstellar medium and the speed of the craft. So that's one possibility, but it's still a very difficult problem to somehow power the craft during its voyage.
Back down in the front row.
If you hit interstellar dust, won't there be a momentum transfer that will tend to throw it away?
Yes, so it could potentially just destroy the craft if it's a large dust grain. But it also could change. It could also spin the craft. Yeah, it's a difficult problem.
So in order to get pictures of the system, which you were mentioning, wouldn't a camera that could get a good enough resolution for the images you want add too much weight to the spacecraft?
So that's one that I didn't talk about, but there's actually some other interesting new emerging technologies on that front too. So there's these things that I might have to picture this somewhere. But at any rate, we can talk about this more later. But there's these new cameras called Fourier capture arrays that have been invented in the last 5 years or so, and they're super cool. Basically, it's a totally flat, on a chip that doesn't need a lens in front of it. So there's no optics involved. So that means you can actually build sort of a giant wafer camera that doesn't have a lens in front of it. So yeah, so there are ways around that.
So I'm wondering, is it possible for you to have maybe an exawatt laser based on the material that you were showing that it can take so much, essentially so much power? Would it be possible to just have an exawatt laser and have it go at 0.5 C if we wanted to?
I think that comes down to a laser problem rather than a material problem.
Okay. It's also a money problem. Yeah.
So you at the end of that road.
I actually have two questions, really quick. One, how would attaching a laser to a boom to serve as propulsion, how would that affect the spacecraft?
So there's been a couple of looks at ways of imparting momentum to the spacecraft with lasers and biobeams in it. It just takes a lot of power. You can imagine that
Right.
The example you gave of like a laser pointer for, what was it, a week is an ant.
Yeah.
Okay, so you can imagine there's not a lot of photon pressure and something like that. And to get a significant amount of photon pressure takes a lot of power. And we don't have a lot of power. So it's just really tough to make that work.
All right. And what about TRAPPIST-1 versus Alpha Centauri?
Yeah, the TRAPPIST system is also an interesting target as well.
Something like this.
So when do you expect like the first prototypes?
Now.
Yeah. Like with laser shooting, like.
So there's already lab experiments being performed to test all the scaling relations for laser propulsion. Zach just passed out the.
Sort of thing, like.
That's definitely a decade or so off. Probably, but I mean,
it could be done sooner than that.
Yeah.
It depends on if, well, so there's actually some interesting lasers out there that the DoD owns that were originally developed for shooting satellites down. And, you know, if they would, you know, help us out. I think there's possibility for some kind of auto. No. Out in the desert somewhere.
We're going to only have time for one more question. I'm sure you can like chat more afterwards, but we'll have to wrap it up. So, yeah, right on the front row.
I work for a semiconductor company, and I'm curious. The boards that you put up on the ISS already, what kind of testing did you do in lab to make sure those components would actually survive space conditions? Because we test down to minus 40 C, and it's a lot colder than that for semiconductor chips.
So we've done a lot of thermal stuff, actually. So I've done crazy things to those boards. I've literally had them operating like sitting in liquid nitrogen and then like from an oven. So I've had them operating with the solder on the board molten in an oven.
The solder was molten?
The solder was molten and they were still transmitting.
I need to talk to you later.
No, I mean, it's probably terrible for the semiconductors, but like I'm sure their lifetime is going to be terrible, right? They're gonna just die, but they do work under insane conditions. At least, you know, it's well outside spec and they do crazy things, right? So like the little LED that was green turned yellow, and you know, it's probably in a different band gap and stuff.
Yeah.
And you can watch on the receiver, if you watch the waterfall plot, like the frequency just goes as it heats up. So it's definitely, you know, not recommended, but they work under extreme, pretty extreme conditions. It's pretty reliable.
All right, well, the waiting people in the control box are telling me to wrap up. So on that note, let's thank Zach.